Saurabh Jishwal, could you please mute your microphone? Thank you. Yes. So in the, we have almost completed our discussion on diodes and diode circuits. In the last Saturday, we had an additional class, right, where we have solved the remaining problems from practice paper 1. So please, if I think you all of you have gone through the practice paper 1, the solutions are also been uploaded. Yesterday, I have also posted one video on passive, which is on the passive filter. So please go through that video. Hmm. After today's class, immediately I will post some of this is only one lecture, so it cannot have like, so many problems, and so they can be asked from it. So some problems as well as their solutions I will immediately post after this class. So please go through that, and if you have any doubt, then in Wednesday's class we can discuss that. Right.
Excuse me, sir.
Hmm. Yes,
Sir,
please, quickly.
lecture the continuation of the video lecture that you shared yesterday.
No, that is, yeah, you can say it continuation from on the, but this is type of, bit a small discrete topic, which is on filters. Filters we have used, right, in our half wave as well as the full wave rectifier, but it is more on different type of, there we have used only RC filters, but here there are different types of passive filters. Okay, how
So,
to calculate their output, what would be their frequency response and all these things, huh?
yes, sir, but yesterday you posted in the night and we are unable to go through that video. So, will
Ah,
it be?
no, 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 no. Yeah, today's lecture is not a continuation of that. Okay. Today is, this lecture is the continuation of, you can say, our Wednesday's class, because Thursday, I think we had an tutorial class, right? So, tutorial class, na? So, this is a continuation of last Wednesday's class. Okay.
Okay, sir, thank you.
Okay. So here, so we have almost completed our discussion on these diodes and diode circuits. So, but before we completely say like we have complete means we say that we have completely finished our diode circuits and diodes this chapter. So there are we have so far discussed about these things, right? We have considered these PN junctions, like PN junction diode. Then we have also discussed about this Zener, right? And all so these two different types of diodes we have seen how they what is their applications in the circuit, how they behave. Okay, these are the these two are the major thing that we have to look into for our numerical problems and all these things. But there are other types of diodes as well. I think for the sake of completeness, we should also know at least the very basics of it. Them, how they operate, which bias they operate, what is the working principle, very briefly. Okay, and that is the whole that is the motto. You can see actually there are 4 different types of diodes. So we will try to complete it to only within this one page only. Okay, so we'll not spend much time, and once we finish it we will start the bipolar junction transistor or BJT. Okay, so to start with the solar cell, solar cell, all of you have heard, you have seen. Now the solar cells has become even more and more popular. Maybe in the future it will become even more popular. Not maybe, it has to be, right? Because it is the source of one of the source of this renewable energy. We can convert our solar energy to electricity, and we can store it. Right? Battery technologies are also improving day by day. So that is also important. One is the generation, and the other one is the storage. Generation is one important, but the storage is also important, because maybe otherwise during the daytime only we'll get the energy, right? But the night, if you want, you cannot get the energy. So you have to store the energy, and that is done by storing the energy in a battery, right? Like, okay. So this solar cell basically a PN junction. Okay, so you can see this is a PN junction where and you just connect this PN junction with a load. Okay, with a load. So here we have represented this load using the resistance, load resistance, right? So when you form this PN junction, there will be an space charge region or the depletion region, right? And there will be mobile charges here, positive and negative on this side. There will be electric field, right? I'm like directing from this N side to P side inside this depletion region, right? Now see what will happen when some light, is fallen on this PN junction. So generally, this light, we cannot restrict the light only to this depletion region, but it will fall in the total PN junction region. But what is most important is the region which is close to this depletion region. Okay, so only this region is important for us. Okay, so here when this light falls, then you know that when this light falls, it is basically an energy, right? So it will form additional electron and holes, like an electron and hole pair actually, because when an electron would be generated at the same time, one hole will also generate, right? Because when the electron will be coming out of its covalent bond, that place one hole has to be there, right? So this light will create electron hole pair in this depletion region, right? And when that electron hole pair, which is also called as EHP, electron hole pair, okay, this is generated inside this depletion region, then see what will happen. This is hole, say, and this is, say, electron, right? This is hole and this is, say, electron. Oh, what is happening? Okay, now due to this electric field, this hole will try to move in the same direction of this electric field. Hole will try to move in this direction, and this electron will try to go opposite to the electric field. So electron will move in this direction, right? Okay, so hole and electron, they will be separated out by this electric field, which is an inbuilt electric field, right? And see, as a result, what is happening? Due to the flow of hole from this direction to this direction, current will flow in this direction only, right? This is the flow of current, this is the direction of flow of current. Current will flow in this direction. And due to the flow of electron in this direction, current will flow in this direction only, right? So you can say the total current, there will be a resultant current, right? Because of this flow of or segregation of this separate out of this electron and hole from this depletion region. So this current has to, come up and it has to flow through this, right? Because like it needs a complete path, right, to flow. So when it will flow through this, it will create a voltage drop across this, right, this V. So you can see when this light falls, it generates one current, and in the external load that will create one voltage. Now, if this voltage is sufficient enough to charge your battery, then you can use this voltage and charge your battery. So this is the whole principle of the basic principle of the solar cell, right? And mostly these solar cells are made up of this silicon, right? Silicon is the mostly available, right? Whatever you have seen mostly on the rooftops, they are basically made up of these silicons, okay? And but there is also some concern, that is the efficiency of this. The efficiency of the silicon based solar cells are not that great, okay? So but the cost wise, they are cheap. They are cheap, but their efficiency is less. But that is okay when we are installing it on the rooftops. But suppose in some applications where the efficiency is if the efficiency is the most priority, means you have to give most priority for the efficiency. For example, for the space stations, okay, or maybe some for satellites that you are sending. So there, weight is the important thing, right? You cannot, give a huge load on a satellite just because of the solar cell, right? So for those cases, what we generally use, we use this defined compound semiconductors, compound semiconductor based solar cells. They are used. For example, gallium arsenide based on the solar cells, and their structures is bit complicated, so we are not discussing. They are basically heterostructures, like tandem in nature, and they are generally used to make energy in those satellites or maybe in the space stations. Okay, so you understood from here the basic principle of solar cell and how they operate and what they are made up of. Okay, then we can quickly move to the next one, which is this photodiode. Okay, photodiode operation is almost similar to that of solar cell, but only difference is that here in photodiode, or photodiode is also called as photodetectors. Okay, so this maybe I should write it here. Photo detectors. Okay, so here what happens when some light falls, okay, and you have actually you have a PN junction which you have intentionally reverse bias. So you can see you have reverse bias this, right? And you have a load resistance here, or maybe like to limit the current. And when the when this light falls on it, then what will happen again? That electron hole pair generation will happen, and now the electric field is much more compared to the solar cell, right? Because here you have applied additional external battery, so the electric field, that magnitude would be much higher compared to the this solar cell, right? Whenever this electron hole pair is being generated, that hole pair will be immediately get separated, right? That will immediately get separated uh, because of this electric field. Okay, and that will create a voltage drop across this, because that will create a current which is called this photo current, right? Photo current, and that photo current will create a drop across this resistance. So you can use this current, and you can identify whenever this current flows in this circuit, so you understand that some light has fallen. So it is basically the principle of photo detector. So light falls, it will detect that light. Okay, so this is the basic principle of this photo detector. So here also you can make these photo detectors with the silicon and also with some compound semiconductors. No issue in that, right? Now, if we move to the third segment of that, so here it is the light emitting diodes or LEDs. I think all of us are quite familiar with these LEDs. We have seen this LEDs
Sir,
in our daily life. Yes.
sir, in photodiode, what is the use of keeping it in reverse bias? We can also keep
What
it
is
in forward bias, no, sir.
yes? The thing is that the current that you will get in the photodiode, that will be much higher if you keep it in the reverse bias. Okay, and also the important thing is that the promptness that you will be getting. Okay, because here the electric field is more, light falls, immediately separates out. Immediately, suppose you want to, whenever light falls, the siren should go on immediately. So you can use that here. Okay.
Okay, sir.
So now in the light emitting diodes, okay, it is also an PN junction diode only, but there is slightly different, means this PN junction, the material wise, it is slightly different compared to the PN junction that we have studied so far, because this PN junction has to be made up with direct band gap semiconductors. Okay, and unfortunately silicon is not a direct bandgap semiconductor. So uh, if you have to make an LED, then silicon is not the choice, right? You have to use some other material which are direct bandgap. For example, gallium arsenide, gallium nitride, they are direct bandgap material, right? So what do you mean by direct bandgap material? So in direct bandgap material, okay, to say it in a simple words, it would be like when an electron. Okay, let's see from here. Okay, so you have forward bias. So remember that LEDs are can emit light when they are in the forward bias. So you have to forward bias an LED. So you can see here plus minus, and this is one resistance been connected to limit the current through this through this LED. And so when this is forward bias, so these holes are injected from this p side to n side, and these holes will go through the diffusion region. Electrons were injected from this n side to p side, and that will be injected through this depletion region only. And in the depletion region, they can recombine. Recombine means one electron and hole, they can recombine and make and become the covalent. That electron can again go and sit in the covalent bond. But during this process, what is happening, just think about it. When it is an electron, so it has some free energy, right? But when it is becoming and or enclosed within a bond, that energy has been lost, right? So how that energy can lose, depending on that, semiconductors can be divided on this direct by into two sections. One is the direct bandgap semiconductor, and the other one is the indirect bandgap semiconductor. So in direct bandgap semiconductor, what happens during that transition? So during right? For example, let's see that this is the valence band and this is the conduction band, right? So this is that energy scale and this is the distance x, right? When an electron is coming out from this, have sufficient energy, it can go to the conduction band and become an free electron, right? And at the same time, in valence band, you have created one hole, right? You have created one hole. So this is the hole and this is electron, right? Now when this electron, free electron and this hole get recombined, then there's this much of energy, right? This much of energy have to dissipate somewhere, right? So in direct band gap semiconductor, this transition occurs without change in their momentum. Okay, their momentum will not get changed. So as a result, this recombination, when that happens, the extra energy will be radiated as h nu or as a photon. However, in indirect band gap semiconductor, when the same transition occurs, there will be change in momentum. So as a result, what will happen? This will not result in a generation of photon, but it will create a generation of this phonon. Phonon, huh? Phonon. So phonon means basically, light is vibration, and due to this, it will create additional heat in this. Means it will be in the indirect band gap semiconductor, this energy will be radiated as heat, whereas in direct band gap semiconductor, this energy would be radiated as this photon, okay, or light. So this is the basic difference between direct band gap semiconductor and indirect band gap semiconductor. And this part is not, this is not a part in your syllabus, but just to give an illustration, like, is basically, this is, sorry, this is E versus X diagram. Okay, this is a band gap. Similarly, if you do, electron wave particle nature, from that, if you use the Schrodinger and this find what is the ek, k is the this wave vector. This wave vector, if you plot this, then basically it looks something like this. Like conduction band, platinum will look like that. This is the valence band, it will look like this. This separation is this band gap. And here, if you see for direct band gap, the conduction band minimum and this is called conduction band minimum, and the valence band this maximum, they are in the same line on this case. So when this electron can come from here to here, it will not create any change in, or it will not experience any change in momentum. So whatever that energy is there, that will be radiated as this photon. However, when if you see for indirect band gap semiconductor, here this ek diagram is looks like this. Okay, here you can see this clearly, this minimum point and this maximum point, they are on the not in the same value of k, right? So if there is a transition, that transition would be by changing the momentum, and that change in momentum will create a lattice heat. So the energy has to be dissipated, but the dissipation would be in terms of heat. So example is this silicon, so which as a result, all this optoelectronic devices, means which can emit light, you will see they are mostly made up of these compound semiconductors: gallium arsenide, gallium nitride, indium phosphide, by all these things, not by silicon. Okay, so this is the basic discussion on this, light emitting diodes. And also remember, I think you should remember here, this LEDs, to emit light, it has to be, forward bias. Whereas for other two, you have seen this, solar cell is basically no voltage has been applied across it. For photo detector, it is operated in the reverse bias. Right. Yeah. Yes.
Sir,
Huh.
sir, what is K in the graph?
K is the wave vector. Okay, so you just take it as a like K at this moment only. Okay, this is called the EK diagram. Huh? This EK diagram. Hmm. Okay. Okay, this comes from bit more complicated solutions. Okay, this is just to illustrate. Okay, you can just find it EK diagram. This is just to illustrate that this minimum point and this maximum point here, they are on the same position, whereas the same K value. Whereas for this indirect, they are not in the same K value. Okay, this is just to illustrate to you that as a result, all these semiconductors are direct band gap semiconductor, and these are not in the these are the indirect band gap semiconductors. Okay. Now there is another type of diode which is called this Schottky diode. So Schottky diode, before you go to Schottky diode, so we have we are quite familiar now with the PN junction diode, where one side is the same, maybe the same silicon material only. One side doped with P type and the other side doped with this N type impurity. N type impurity means one side acceptor impurity, one side donor impurity, right? And that basically forms this PN junction. And you know this PN junction, how does it operate? When you forward bias this PN junction plus this minus, this holes from P side injected to this N side and become the minority carrier. So you can see that injected excess holes, right? We have discussed this in our class, right? Similarly, these electrons will also inject from this N side to P side and become the minority carrier on this P side, right? So this will be the profile of this. And then also you have seen, if we now immediately change this polarity, but if you immediately reverse this polarity, make this negative and make this positive, then we have seen this current conduction through this PN junction will not stop immediately, right? But it will take some time, that storage time and then decay time, right? Like that, right? So based on this, so you have to give some amount of time before which this PN junction can turn off completely, right? So and that happens because of this minority carrier, these holes on this N side and these electrons on this P side only. But you think about it, if we can now make a junction between some metal and some semiconductor, say this N-type semiconductor. So this is metal and N-type semiconductor, right? So between these two, again, one barrier will form, right? And this barrier will also be rectifying in nature. Okay, that barrier will also be rectifying, means you will get one side current will conduct, other side it will try to block. But here the advantage would be when you forward bias it, means suppose when you positive and when you make it negative, the current will flow. Okay, the current will flow due to the injection of electrons only, and these electrons from this metal, when it will go to this N side, this N side electrons is also the majority carrier, right? It's not the minority carrier. So as a result, there will be no storage of no question of storage of any minority carrier. So as a result, this type of this storage time, that thing would not appear, right? This type of storage thing will not appear in case of this Schottky barrier diode or Schottky diodes. So you can see from here, this current flows due to the flow of this majority carriers only. No minority carrier storage, because there is no concept of minority carrier here, because electrons are injecting from here, which is a majority carrier in this N side. If it is a P type, then it will be the other way. Okay. So as a result, the speed would be higher, right? Because here, this direction you cannot do anything, right? You have to, your applied pulse, if your pulse width is lower than that, then during this time, your diode is not actually completely off. But here, so that means you have to keep the pulse width sufficiently long so that that width is more than this storage time. But whereas for this Schottky, as there is no question of this minority carrier, this minority carrier storage, so it can be operated at a higher speed. So that's what when you need some rectifying action with a higher speed, we prefer this Schottky barrier diode instead of this PN junction diode. And the only difference is, instead of this PN, it's basically a metal and semiconductor junction. And if you have to compare the IV characteristics between this yes.
So could you please re-explain this minority carrier storage concept? I could not understand it. So.
You could not understand it. Okay, I think have you seen that class means that lecture where we have discussed this one, storage time in PN junction diode? Okay, if you cannot recall, maybe I can. So please go through that. There we have discussed it in more detail. So to discuss it quickly, say when this is positive and negative, this diode is forward bias, right? Then do you agree that the injected carrier profile would be like this? Yeah.
Yes, sir.
Okay. Now suppose we have suppose we are applying this type of pulse. Okay. So during this would be the profile of this charge in both P side and N side, right? Now suppose we consider this. Now all of a sudden you change from this positive hub to negative hub, right? Then when you make negative hub, then actually what you are doing, you are making this negative and making this side positive, right? But when you have done that, so this is positive, now this is negative, right? But you see that still you have this much of excess electrons, sorry, excess holes on this P side, and this much of excess electrons on this P side, which are actually called the minority carrier, right? Which are actually minority carrier. And this minority carrier cannot disappear all of a sudden. It also needs some time, to this excess holes to move from this side to this side, and these excess electrons to from p side to n side. So that time is called the storage time. Okay, because during this time, what will happen? You have now reverse bias this PN junction, so you are expecting there will be no current. But due to this movement of this additional stored charges on both p side and n side, the current will not become immediately zero. But for certain amount of time, the current would be keep on flowing, and then slowly that current will decay and become zero or close to IS, reverse saturation current. So this time is called the storage time. Okay, and because this is happening because of this minority carrier storage on for this PN junction, whereas for Schottky there is no minority carrier storage, so this problem would not arise there. Is this clear to you now?
The N side would anyways have holes, right? Even in the Schottky barrier diode.
Could you please repeat your question?
So although we've replaced the P side, but the N side would still have injected excess holes, or would it not have it?
No, it is not happening because see this N type, suppose you have doped with 10 to the power 16 per centimeter cube, right? Okay, say here the same thing, 10 to the power plus 16 per centimeter cube, right? So what will happen here? This is 10 to the power. So what 10 to the power 4 would be the around number of holes, right? Here. So this is the equilibrium concentration. So, but this is what you are getting. So this is the excess. That's what I'm writing. Injected excess holes. This is the excess amount. Whereas here as well, so this would be the number of electrons, and number of holes would be 10 to the power 4 only per centimeter cube, right? But when you are forward biasing this Schottky, what is happening? Only electrons are injecting here, not holes are injecting. So this number is not changing. So this number will be fixed at 10 to the power 4 only. But here, see, in equilibrium, this has to be 10 to the power 4. But maybe for here, this may go up to say 10 to the power 15% near to this junction. Okay, which is much higher compared to the equilibrium value. Is it clear to you now?
Yes, sir. All right, thank you, sir.
You are welcome. So if you see this I and V characteristics of like compare both PN junction, then but I should here mention as well, like this also depending on which material you are using, what is the gate metal work function. Depending on that, there might be a slight change of these characteristics, right? But typically, if you consider a PN junction and Schottky diode, its characteristics would be like this. For PN junction, the V gamma is expected to be bit higher compared to the Schottky diode. The reason behind is that for Schottky diode, the leakage current is that is this IS is expected to be bit higher compared to the PN junction diode. So as a result, again I'm saying this is typically because if you now change this metal, change this work function, then you can control this IS and V gamma as well. So again, this is a typical representation between Schottky and like PN junction. So here also from this you can see using both Schottky and PN junction diode, you are getting one rectifying characteristics, right? So it does mean that by using Schottky diode as well, you would be able to get an rectification. Like you can use it with half wave rectifier, full wave rectifier. You should be able to make, right? Okay. Okay then.
Sir, is transistor is also in syllabus?
In which syllabus?
I mean, Wednesday exam.
No. It's the diode and filters. Okay. So this bipolar junction transistor, or in short, it is also called as BJT, right? So why it is called bipolar, right? Why it is called bipolar? Because you will see that in the when you discuss the conduction mechanism of BJT, then you will see both electrons and holes participate in carrier conduction. So that's why it is called bipolar. Whereas when you will discuss this MOSFET after that, after once you finish this BJT, then there you will see for MOSFET, it is the current conduction to be either through the electrons or through holes. Okay, not both. So they are called the unipolar. Okay, they are unipolar devices, but this BJT is a bipolar device. And here then after that you can see there are junctions. So obviously that's related to the PN junction. And transistor is the transfer of resistance, that also you will see why it is called transistor. Okay, so this BJT, if you have to represent in a block diagram way, then it looks something like this. Say P N P. Okay, in block diagram it looks like that. So it is basically a PN junction. So you can consider this as a PN junction, right? You are familiar with that. And this is another PN junction, right? So this is another PN junction. So two PN junctions connected back to back. So you can think the structure similar to this, right? It's a PN junction, right? Now, maybe some of you can also say why to place the diode like this. I could have placed the diode in this fashion as well, right? I could have placed the diode in this fashion as well. Yes, you are right. So, and you can do it absolutely. So if you do it, now you see it would be like this, right? Here it is N and this is P, this is N, this is P, this is N. Yes, this is also another BJT, bipolar junction transistor. So BJT can take this form or BJT can take this form, right? But you don't think that if you then take two diodes, okay, one diode like this, and take in diode and another diode in your laboratory, and just connect these two like this, and that basically makes one BJT. That is no. Okay, it does not. It does not act like an BJT. Why it will not behave as a BJT or bipolar junction transistor, that would be clear to you when you discuss in bit more detail the structure and the doping concentration on the different ion sites. Then it will be clear to you. But remember that two diodes connected back to back cannot form one bipolar junction transistor, right? So if you take this PN like this and then NP, so this is one BJT. Or if you take NP then PN, this is another BJT. So this is called PNP bipolar junction transistor. This is called NPN bipolar junction transistor. So this is P. Maybe I need some space here. So maybe I will write below. This is PNP BJT. And this is that NPN bipolar junction transistor. Okay, and here so you can see that there are three regions are there, right? PNP. So we should also have three terminals, right? To connect to this N side, P side, and this side. Similarly, here also we should have three terminals, right? These three terminals are called as E, B, and C. E, B, and C, where this E stands for emitter, B stands for base, and C stands for collector. So this B is base, collector, emitter, right? Is it clear to you? Okay. Now you see there are two PN junctions, right? One is this PN junction and this is PN junction. This is another junctions. So these are junctions. So two junctions are there. And one PN junction, this suppose if you consider one, this is an PN junction, right? or maybe I should not use this you might get confused with this then. So we are consider, let us put it in the block diagram. So this is a PN junction, right? Now you can probably apply here positive and here negative. So that way it will become forward bias, or you can apply here negative and here positive. That would make this PN junction an reverse bias, right? Similarly, here each of the junctions can be either forward bias or reverse bias, right? And suppose if you consider this one is forward bias, then the next one for this to be forward bias, this can be either forward bias or reverse bias, right? Similarly, if it is reverse bias, then also this junction can be forward bias or reverse bias, right? So in total, then you understand there will be 4 modes of operation, right? You can make this forward, this reverse, you can make this forward, this forward, you can make this reverse, this forward, you can make this reverse and this also reverse, right? So 4 modes of operation, 4 modes, depending on biasing of PN junctions.
Sir, how do we differentiate between emitter and collector?
Yes, please give me some time. We are coming to the structure, huh? Then it would be clear to you.
So to get the different modes, we apply different voltages at E, B, and C. Or is there
Exactly,
some other-
exactly,
Oh, okay.
exactly.
All right.
We apply different voltages between these terminals, okay, to make these junctions either forward bias or reverse bias. Fine. Okay.
Yes, sir. Thank you, sir.
Okay. Okay. I think let me answer that question. Like one of your friend has just now asked that how do we differentiate between this emitter and collector? Because you can see for this NPN transistor, this is also N side, this is also N. Well, this is also N type semiconductor, this is also N type semiconductor. Then is there any difference? Or if you consider PNP, then here you can see this emitter is also P, this collector is also P. So is there any difference? So 1 minute. So this is basically this one, right? Okay. So if you see the transistor structure, means the BJT structure that we have discussed using a block diagram, which is quite simple, right? N, P, N. But actual fabricated structure, it is not that simple. It's a bit complicated. So you can see this is a total semiconductor. Say this P-type silicon substrate. So this is an P. Okay, which one color I can use? Okay, say this is an P-type silicon substrate to start with, right? Then on top of which you made some layer. Okay, don't ask me right now why this layer is being used right now. So this is N plus buried layer is there is, I mean, some layer is being formed which is N plus plus, means more plus means more heavily doped. When you say this N, so what is the difference if it is N, N plus and N plus plus? So that means N plus plus has a much highest doping, like this, doping, right? So from doping wise, you can differentiate it like this. Plus plus means it has a more higher doping than this plus, and compared to the N plus, means N plus has a higher doping compared to N. Right, so it is very heavily doped, this layer, right? So on top of which you see that we have made one. So you can see here this is an N region. This total region is the N type semiconductor, N type silicon, right? Inside this N type silicon, you have made another, means you have opened one window, do a doping. This process is called doping, okay, and made this particular region only this P type. Okay, so this is P plus. So that means you can understand from this N side, this P side doping is bit higher, right? So you have made a P type. This is called this P plus well. Okay, this because it looks like a type of well, right? So it's P plus well you formed. Then after that, you create another opening here and create another N plus plus well here. So you can see inside that N plus plus well it formed. Right. So if you are considering this N, PN bipolar junction transistor, then you can see this N plus plus. This is the first one. This N plus plus. Then you take a contact, make a deposit metal, take contact like this, and separate one contact from the next contact by this silicon dioxide, as well as some physical separation between these two metal contacts. So you can see that physically they are separated, and these contacts are also, some part of the contact is also, staying on top of the silicon dioxide, because to prevent, right? Because this, if the silicon dioxide was not there, then maybe if this metal is shorting this one and this side, then what would happen? Then basically P plus and N, it will be shorted by using this metal, right? So to prevent that, we use this type of silicon dioxide, and keep some part of the silicon dioxide here, and only in between this region we create, we open and create a contact with this P plus region. Okay, other region you can see it is like, this is for the, while fabrication, this type of safeguards are being used. So here you can see this emitter. So you can see this emitter. You understand this is N plus plus is the emitter. Then this, there is a P, right? So this is emitter. Then this is P plus region, which is basically the base, right? And obviously N plus P, this, then outside is this N. So obviously that N is this collector. So this N is the collector, right? And this collector is, sitting on top of this N plus plus buried layer, which is used to reduce the collector resistance. Okay, because see, like, then you think from this perspective, this is N plus, this is P. So when the means, so basically the device, here you have considered type of one dimensional, that current can flow like this, like, type of one dimensional but here you can see it is type of 2D picture, and here current can flow from here to here, right? Because if you see this everywhere, it is this PNP, it is sorry, NPN, this is also NPN, this is also NPN, right? Everywhere it is NPN. So the total thing is this bipolar junction transistor. Now if you try to correlate this structure with this, then basically you can do the correlation like this. Okay, you take a, like, consider a box here, then this is this N plus plus region, this is this P plus region, and this is the N region. So this is that emitter, this is that P plus, this is that base, and this is that N, this is that collector region. Okay, so this is basically what, if you consider a slice like this, then it's basically will be close to the block diagram that we are using, right? So you understand at least type of, broadly, like why this N plus plus buried layer is being used, because if the electrons are coming from here, now this N plus means it is not heavily doped, right? So it is not heavily doped, it has a higher resistance, right? So if these electrons are coming out from here, then if there is some region where the resistance are lower, then the current will take that path, right? So current will take this path and go out from this collector like this. So that is the thing which has been used. Right now, here is this collector, right? So you can take one contact directly with this N plus from the top, but rather doing it, what we do, we just make another N plus region to get a better contact, and take a contact, make a ohmic contact with this, and get a connect. Means this is our third terminal, which is the collector. So it is the emitter, it is the base, and this is the collector. Now quickly, if you have to consider, suppose the doping concentration, then suppose we are taking a line along this. Okay, we are taking a line along this, this line, and want to do the doping concentration. Then the first one, you can see I have plotted this type of small lines here, right? So this is the emitter. So for emitter, the doping concentration is like this. This is for emitter. Then for this base, so for base, doping concentration is like this. Okay, for collector, the doping concentration is like this. So we are plotting only up to this. Okay, because this N plus plus buried layer is not that way, participating in transistor action, but what it does, it's gives some additional advantage in terms of reducing the reducing the collector resistance, but not in the physical operation of this transistor. So you can see the doping concentration, emitter, base, collector, right? Now, I think it is quite clear to you that, how do you separate out or differentiate out this emitter and collector, right? So emitter is the region where you have the highest doping, and collector is the region where you have the lowest doping, right?
Sir, the C is also connected to N++.
Could you please repeat?
Sir, the collector terminal is also connected to N++ region.
Collector terminal is, yeah, you are right. Collector terminal is connected to N++. Okay, this is true. This is just because you have to reduce the contact resistance between this metal and this N region. If you have suppose if you have removed this as well, then this device would also show the transistor action. It's not like it will not show, it will also show the transistor action. But to get a better transistor action, but there will be some drop, some voltage drop will be occurring across this C and this junction. Okay, so to prevent that, we connect this N++, but that's what I was trying to explain. If you consider this block, this is actually this transistor block, which actually determine the transistor action. So this N++, P and N region, not this. Okay, once the current has, once this current has reached to this N+, or once the carrier has reached to this N, for example, for this, suppose electrons has reached to this N side. So this, what it will do, it will just go through this, right? This will not determine that how much electrons should come from this P to N or this N+ to P. This, whatever it will come, it will just collect it. Okay, so in other words, what you can think of, right? This is you are making a door or bit, you are making a door which is bit bigger, so that whatever electrons it is coming, you are able to collect it. Okay, but whatever electrons are coming, that is not determined by this door, but by the other doors. Okay, so you are making sure that whatever is coming, you should be able to collect it. So is that part clear to you?
Sir, can you repeat the explanation for buried region, buried layer? I mean, the purpose of it.
Buried layer. Okay, buried layer is to reduce the contact resistance. Okay, so suppose this electrons, okay, for here, what will happen when you basically it will forward bias this emitter base junction. Okay, so the electrons would be injected, right? So that suppose the electron is injected like this, it is Pn, and so then after it will cross this base and it will reach this collector, right? So when we reach this collector, if it has to come, just think in this way, if it has to come all together and this way, then this is the N region, right? N region means low dope region, right? Low dope region means it will offer a higher resistance, right? But if you have some region which is below that, which is also N++, it has a lower resistance, right? So when these electrons will see there are these different paths are available, it will try to take this path and go. Okay, or in simple word, just to reduce the collector resistance.
So the electrons will enter the N++ buried region and travel horizontal. I mean, from the diagram, it will travel horizontal and
right, and then it will go up, right?
Okay.
Okay, so this is the the way the transistor has been actually practically made. And here one thing you have to remember, that this base region has to be very thin, right? Very thin. This base. If this base region is not very thin, you will not get the transistor action. Okay, to get the transistor action, you should make the base region, I think, depending on the time is 10:52. If I start the explanation of okay, I can possibly complete the circuit with this one, and because I could not probably now today able to explain this operation, time is not enough. Maybe I can do it in the next.
We have an exam after this.
Yes. I know that. So I will end up here only. Okay, so remember that this base has to be very thin. If the base is not very thin, then you will not get the transistor action. So that way you can see this, even though we are plotting, even though we are drawing the structure like this, N P N, but these bipolar junction transistors are actually not electrically symmetric, right? Not electrically symmetric, right? And that's also probably you can understand also better, you will understand it better once we explain the operation, right? Because you can see from here this doping concentration itself are different, right? And at the same time, if you see the area, that is also different. See the area of this emitter, right? And see the the total area of this collector, that is also different, right? So that way, yeah, if you interchange this emitter and collector, right, your performance will degrade like a lot, and it is not advisable to do so. Okay, so and quickly let me do just the circuit symbol and we will finish with this. So the circuit symbol of this bipolar junction transistor, this is for this NPN type. So for NPN, the symbol we use is like this. This is collector, this is emitter, this is base, right? And for PNP, we use the symbol like this: emitter, base, collector. Okay, so this emitter, in emitter terminal only, we will give these arrows. Okay, so here you can see it for NPN. In emitter terminal we have an arrow, and in PNP also we have an arrow in the emitter terminal only, right? And this arrow indicates like the flow of current, right? When this base to emitter junction is in forward bias. So base to emitter junction is in forward bias means you have to forward bias this PN junction. That means you make it plus, make it minus, right? This. So that way you can see the current will flow through this, right? So basically you are making this plus, making this minus. So your current is flowing like this. So that's why the arrow is like this. And for PNP, you make this PN junction forward bias. So then you have to think of a battery like this. So the current will flow through this. So that's why the direction, the arrow direction is like this. Okay. So yeah, this is the notation, and we will use this notation or the circuit symbols when you are using this bipolar junction transistor in our circuits. Okay, we will not use this block diagram, this representation. Okay, I think with this we will stop because you told you have an exam today. Okay, so and please go through the that lecture that I have posted on passive filters. Okay, and let me know if you have any doubt on it in the next class. Okay, and if you have any questions like before we end. Okay, if you do not have any question, then I think thank you.
Thank you, sir.
Thanks.
Yeah.
Thank you, sir.